Hello everyone, welcome to this lecture. So, we will continue our discussion regarding the impossibility or the impossibility proof or the necessity proof for the necessity condition for the existence of perfectly secure Byzantine agreement. So, in this lecture we will complete the proof and we will show that it is not possible to design any perfectly secure Byzantine agreement protocol if this condition n is less than equal to 40 holds. That means, the condition n greater than 3t is necessary, and recall that we all the protocols that we had seen till now, there we assume that the condition n greater than 3t holds. So, let us quickly go through the proof for the impossibility of perfectly secure Byzantine agreement for 3 parties tolerating 1 corruption that we had discussed in the last lecture. So, the proof was through a contradiction. We assume that suppose there is a protocol say pi 3 BA which allows 3 parties ABC with protocol codes PQR respectively to solve the Byzantine agreement problem, even if one of the 3 parties ABC could get corrupt, such that the protocol pi 3 BA has the liveness, validity and the consistency property. Assuming such a protocol pi 3 BA exists, we saw that we can compose the protocol pi 3 BA and we can create a system, a hexagonal system S, where we now have 2 copies of A 0 and A1 with inputs 0 and 1 respectively and running the protocol code P, 2 copies of B 0 and B1 with inputs 0 and 1 and running the protocol code Q respectively, and 2 copies of C, namely C0 and C1 with inputs 0 and 1 respectively, running the code R, such that each participant has knowledge about only its immediate neighbor, but not about the full network. And in this system S, there is no corruption and every party is just participating with its input as assigned in this system S and running the protocol code either P or Q or R, as depending upon whether they are the copies of entity A, B or C respectively. And then we saw that the system S can be visualized as several instances of pi 3 BA being running in parallel. Say for instance, we can take the triplet of parties A0, B0 and C1, and it will look like we can consider this triplet of parties as if we are running this system where A0 has the input 0 and B0 has the input 0 and C1 has the input 1, and A0 will be talking with B0, A0 will be talking with C1 and B0 and C1. Okay, sorry. So, the way we can visualize this as several instances of pi BA being running in parallel is as follows. So, from the viewpoint of A0, its 2 neighbors during the instance of pi 3 BA are B0 and C1. Okay. So, A0's neighbor will be B0 and C1, and that matches with what we expect from the protocol pi 3BA, because in pi 3BA we expect party A to talk with one copy of B and one copy of C. That is what is happening in the system S. From the viewpoint of B naught, okay, we can imagine that its neighbors are C naught and A naught. So, this is consistent with what we expect during one execution of pi 3BA, namely B is expected to talk with C. So, in this case B naught talking with C naught, and B is expected to talk with A, that corresponds to B naught talking with A naught, and we can imagine that we have C1 talking with B1 and A naught. That is the way we can imagine. So, like that we had seen in the last lecture that in the system S we can imagine several instances of pi 3BA being running in parallel, and then we saw various properties, various relationship among the outcomes from those invocations of the instances of pi 3BA and the output of the respective parties in the system S, and then we actually end up showing that in the system S parties may have inconsistent outputs. That means, the system S output is not well defined, even though that should be the case, because we are actually running the protocol pi 3BA several times. That is the way we can imagine the system S. So, that shows that whatever we assume regarding the existence of protocol pi 3BA is incorrect. No such protocol pi 3BA exists. But this impossibility proof is restricted because it is only for the case when we have 3 parties and one of them is corrupt. Now, we want to generalize this proof and show that there exists no perfectly secure Byzantine agreement protocol if n is less than equal to 3t. And again the proof will be through a contradiction. What we will show here is that if at all there exists any protocol, any perfectly secure Byzantine agreement protocol with this condition 3t greater than equal to n, let us call such a protocol as pi 3t sub pi sub 3t t. So, we are taking the case when n is equal to 3t. So, we assume that suppose there exists a perfectly secure Byzantine agreement protocol with the condition n being equal to 3t, then we will show the existence of a perfectly secure protocol pi 3BA for 3 parties with one corruption. But we know that the protocol pi 3BA does not exist, this does not exist. That means, whatever we assumed regarding the existence of pi protocol pi sub 3tt also is incorrect. Okay. No such protocol exists. So, imagine we have a protocol pi sub 3tt which solves the Byzantine agreement problem. It satisfies, it gives you the termination guarantee, validity guarantee and consistency guarantee. Okay. We do not care how many round protocol it is, but what we know is that it has the liveness property. So, say it is an R round protocol, it has the validity property. That means, if all the honest parties in this protocol have the same input, then that is the output, and it has the consistency property. That means, all honest parties have the same output at the end of the R rounds. Now, using this protocol we design our protocol pi sub 3BA, where our 3 parties are A, B and C respectively. Suppose the input of the party A is little a, which is a bit. Similarly, the input of the party B is little b and the input of the party C is little c. Now, what the party A does is the following: it simulates the role of the parties P sub 1, P sub 2, P sub t as per the existing protocol pi sub 3tt. Okay. Assuming that all the parties in this collection have the input A. So, basically what I am saying here is that according to the protocol pi sub 3tt, there would have been a protocol code for P1, there would be a set of steps, set of actions, set of protocol code, a sequence of protocol code for the party P2, and like that there will be a sequence of steps for the party P sub t depending upon whatever is their input. So, party A in our protocol pi sub 3BA actually runs the code which has been assigned for P1. Let us call that code as program 1. Whatever code has been assigned in the protocol pi sub 3t, let us call it program 2, and like that whatever set of steps, actions have been prescribed in the protocol pi sub 3tt, let us to the party P sub t, let us call is program sub t. So, party A in the protocol pi sub 3BA will run the protocol code program 1, program 2, program sub t, assuming that the inputs of the parties P sub 1, P sub 2, P sub t is little a. In the same way, in the protocol pi sub 3BA, party B will simulate or play the role of the party P sub t plus 1, P sub t plus 2, P sub 2 t, assuming that their input is B and they are running their respective protocol code as prescribed in the existing protocol pi sub 3tt. And in the same way, C simulates the role of the last t parties P sub 2 t plus 1, P sub 2 t plus 2, like that P sub 3 t, assuming that all their inputs are small c and they are following the protocol code pi sub 3 t t. Now, when I say simulate, that means according to the protocol pi sub 3 t t, it could be the case that a party in this collection, the collection P sub 1 to P sub t, want to send message to any other party in the same subset. So, let us call these 3 subsets as fancy A, fancy B and fancy C. So, during this simulation, whenever any party in the subset fancy A is supposed to send any message within the subset fancy A itself, then that is simulated by the party A sending the message to itself. Okay. Whereas, if at all there is a requirement that any party in the subset fancy A has to communicate a message to any other party in the subset fancy B. Say P1 has to communicate some message M to the party say P sub t plus 2 as per the protocol pi sub 3 t. That is simulated by A sending the message M to the party B. In the same way, if there is a party in the subset fancy B, say P sub 2 t has to send a message M prime to party P sub 2 t plus 1. That is simulated by B sending the message M prime to the party C, because now B will be, since B is playing the role of P sub 2 t, it will having the message M prime, and since the role of P sub 2 t plus 1 is played by party C, it is party C who should possess the message M prime. So, that is why M prime will be communicated to the party C. So, that is the way simulation happens here. Now, due to this simulation, what we can say here is the following. If we consider the view of the party A in this protocol pi sub 3 BA, and what does view means? the view means all the messages sent and received during protocol execution So, if we consider the view of this party sub A, its view will be identical to the view that party P sub 1, party P sub 2, party P sub T would have in the existing protocol pi sub 3 T T if they would have been running the protocol pi sub 3 T with inputs A respectively. In the same way, the view of the party B in the protocol pi sub 3 B A will be identical to what the party P sub T plus 1, P sub T plus 2, P sub 2 T would have produced with their inputs being B during the execution of the protocol pi sub 3 T T, and in the same way the view of the party C will be identical to what party P sub 2 T plus 1, P sub 2 T plus 2, P sub 3 T would have if they would have executed the protocol pi sub 3 T T and their inputs being C, C, C respectively. So, now what we can conclude here is that since the protocol pi sub 3 T T has the liveness property, protocol pi sub 3 B A also would have liveness. Namely, at the end of the simulation, so if pi sub 3 T T is an R round protocol, it is an R round B A protocol, then party A, after simulating the role of the first T parties for R rounds, output whatever those T parties would have output during the execution of protocol pi sub 3 T T. And since the protocol pi sub 3 T T would have produced output after R rounds, that shows that party A also would output something after R rounds, because each of the parties P sub 1, P sub 2, P sub T would have output something after R rounds. So, the liveness property of pi sub 3 T T implies the liveness property of this 3 party protocol. If the protocol pi sub 3 T T has the validity property, then that implies the validity of the protocol pi sub 3 B A. So, for instance, suppose A is small a is 0 and say small b is also 0 and say the party C is corrupt, then that means in the simulated execution, namely in the execution pi sub 3 B A, what is happening is the first T parties are running the protocol pi sub 3 T T with input being all zeros, and the same way the parties P sub T plus 1 up to party P sub 2 T are also running the protocol assume with their inputs being 0, and they are running the protocol code pi sub 3 T T. So, consider the case when P 1 up to P sub 2 T are honest and P sub 2 T plus 1 up to P sub 3 T are corrupt, and all the honest parties have this input 0 and the corrupt party we do not care. The protocol pi sub 3 T T should have guaranteed that P 1 up to P sub 2 T outputs 0. That comes from the validity property of pi sub 3 T T. Now, if we see the protocol pi sub 3 B A, what is the output of A? That is the same as the output of the parties P 1 to P sub T. So, that means party A will output 0, and what will be the output of the party B? That will be same as the output of parties P sub T plus 1 up to party P sub 2 T. From the validity of proper protocol pi sub 3 t, its their output will be 0. So, B's output also will be 0, and that is all. That implies the validity of protocol pi sub 3 BA. And in the same way, the consistency of the protocol pi sub 3 t, t implies the consistency of the protocol pi sub 3 BA. So, again imagine that among these parties A, B, C is the corrupt party. So, basically the execution of pi 3 BA, and we do not know what is the inputs A and B, they might be same, they might be different. Then in that case, the execution of pi 3 BA corresponds to this scenario where we have a bunch of 2T parties who are honest and a bunch of T parties who are corrupt. The honest parties may have the same input or a mixed bag of input, but due to the consistency property of pi sub 3 t t, all the honest parties, namely P 1 to P t and P t plus 1 to P sub 2 t should have same output. Now, the outputs of P 1 to P t corresponds to the output of A, and output of P sub t plus 1 to P sub 2 t corresponds to the output of B. And since all these outputs are same, that means parties A and B also will have the same output, and that implies a consistency for the protocol pi sub 3 BA. So, what we have shown here is that if at all protocol pi sub 3 t t exists and we have a protocol pi sub 3 BA with the liveness, validity and consistency property, but we know that no 3 party perfectly secure BA protocol pi 3 BA exist. This implies there is no perfectly secure protocol pi sub 3 t t. Okay. And that shows that the condition n greater than 3 t is necessary for any perfectly secure BA protocol. Till now we have seen the characterization of perfectly secure BA in complete graphs. Okay. And when I say complete graphs, I mean we considered a network scenario, we considered an underlying network where every party has a channel or a method to communicate to every other party. And we have just concluded that for designing perfectly secure BA in such networks, the condition n greater than 3 t is necessary. Now, we might have an underlying network which is modeled by a graph which is incomplete. That means, in such a graph there may not be a direct channel, direct communication link between every pair of parties. So, for instance, if I take this party to be A and this party to be C, then there is no direct link between the party A and party C. Any communication from A to C has to go through either this node or one of these two nodes. Okay. So, if in such a network, if we have up to T Byzantine faults, T Byzantine corruption, what would be the necessary condition for the existence of perfectly secure Byzantine agreement? Okay. So, we will focus on the answer for this question in our next lecture. These are the references used for today's lecture. So, the proof that I gave today, it is often called as the player partitioning proof strategy. This is because the way we have completed the proof is we argued that there is no protocol pi 3 BA, and then to show that there exists no protocol For 3T parties, we had divided the parties into 3 subsets, fancy A, fancy B and fancy C, each simulating the role of T parties, so that we get a 3 party protocol. So, that is why that proof strategy is often called as the player partitioning proof strategy. Thank you.